Hello and welcome to Space Historians. I'm truly glad you found your way here tonight, ready to slow down, breathe deeply, and drift into one of the most profound questions we can ask. Not about space, or stars, or galaxies, but about time itself, the invisible river that carries everything forward, the silent framework within which all existence unfolds. Tonight, we're exploring how time began. And that question, simple as it sounds, opens doors into mysteries so deep that even asking them changes how you experience this very moment. Before we begin, I'd love to know, where in the world are you listening from? And what time is it where you are? It's a small irony, using time to locate yourself as we prepare to explore whether time has always existed or whether it had a beginning, a first moment, a threshold before which the word before had no meaning. If you enjoy these quiet journeys through the deepest questions of existence, a like and a subscribe help keep this channel drifting steadily through the cosmos of wonder. And for those who've already joined this constellation of curious minds, thank you. You're part of this voyage, part of this shared exploration of what it means to exist within time. Each episode here isn't just about delivering facts, it's about creating a space where you can contemplate the incomprehensible, where the boundaries of understanding become pathways to awe rather than barriers to knowledge. Tonight's question, how did time begin, is one of those pathways. So as your breathing slows and your thoughts begin to settle, imagine yourself suspended in a moment before moments existed. Not darkness, because darkness exists in time. Not silence, because silence is the absence of sound across duration. Imagine instead a state so fundamental that even the concept of state doesn't quite apply. A timeless origin from which time itself emerged. If you'd like to be notified when the next journey begins, gently press the notification bell. But for now, you don't need to do anything except listen, wonder, and let your mind drift into the question. Let's travel together through cosmology, through quantum mechanics, through philosophy, toward the threshold where time began, or perhaps where it continuously begins with every passing moment. Welcome to the origin of origins. Close your eyes for a moment, not to sleep, though that will come soon enough, but to notice something so obvious we rarely think about it. Time is passing. Right now, this moment is becoming the past. The next moment is arriving. The present is a thin, fleeting boundary between what was and what will be. But here's the astonishing thing. There was a moment, about 13.8 billion years ago, when this wasn't true. When there was no past, no future, no present. When time itself did not exist. How is that possible? How can something so fundamental, so woven into the fabric of reality, have a beginning? And what does it even mean to say time began when the concept of beginning requires time? This is the paradox at the heart of our question. We're trying to understand something using a framework that only makes sense after that something exists. It's like asking what's north of the North Pole. The question contains its own impossibility. The direction north is defined by Earth's geometry, and at the North Pole, every direction is south. There is no north of north. Similarly, there is no before time. And yet, cosmologists, physicists and philosophers have spent decades grappling with exactly this question, not because they expect a simple answer, but because wrestling with it reveals something profound about the nature of reality. Let's start with what we know, or think we know. The universe began with the Big Bang, a moment when all of space and all of time came into existence. Not an explosion in space, but the expansion of space itself. And because space and time are linked, woven together into what Einstein called spacetime. When space began to expand, time began to flow. But what does that mean exactly? It means that time is not an eternal stage on which events play out. It's not a pre-existing framework that was always there, waiting for the universe to fill it. Time is part of the universe. It's as much a creation of the Big Bang as matter, energy, and space. Before the Big Bang, there was no time. But before is the wrong word, because before implies a temporal sequence. It's more accurate to say that the Big Bang marks the boundary of time. You can't go before it because time begins there. It's the edge, the threshold, the point beyond which the concept of past has no meaning. This isn't just philosophical wordplay. It's based on the mathematics of general relativity, Einstein's theory of how gravity warps space and time. When physicists run the equations backward, tracing the expansion of the universe in reverse, they find that space contracts, temperatures rise, and densities increase. Keep going backward, and you eventually reach a point where the equations break down. A singularity, where the laws of physics as we know them no longer apply. At that singularity, roughly 13.8 billion years ago, the universe was infinitesimally small, infinitely dense, and infinitely hot. And time, according to the equations, was not flowing. It was compressed into that single point along with everything else. But here's where it gets strange. Physicists can trace time back to an incredibly brief moment after the Big Bang, something called the Planck time. That's about 10 to the power of negative 44 seconds. 1/10 million trillion trillion trillionth of a second. At that moment, the universe was already expanding, already evolving, already ticking forward. Time had begun. But what about the moment before that? What happened at the exact instant of the Big Bang? At time equals 0? The honest answer is, we don't know. Our current theories, general relativity and quantum mechanics, can't describe what happens at that point. They give us infinities, mathematical nonsense, contradictions. It's as if the universe is telling us that our concepts don't apply there. Some physicists believe this means time doesn't have a true beginning. Instead, it emerges gradually, like steam condensing into water. In the earliest moments, the universe might have existed in a quantum state, where time, as we experience it, didn't yet exist. There was no clear sequence of events, no before and after, just a foam of possibilities, quantum fluctuations that hadn't yet crystallized into a definite timeline. Imagine a film projector showing a movie. What you see on the screen is continuous motion, one event flowing into the next. But if you stop the projector and look at the film strip, you see individual frames, static images separated by darkness. The motion is an illusion created by the projector. Some physicists think the early universe was like those static frames, existing without motion, without time, until something, perhaps the expansion itself, started the projector and time began to flow. This idea suggests that time is not fundamental. It's emergent, something that appears when conditions are right. Just as temperature emerges from the motion of atoms, or wetness emerges from the behavior of water molecules, time might emerge from more fundamental quantum processes. But there's another possibility, one that's both more radical and more comforting. Maybe time didn't begin at all. Maybe the Big Bang wasn't the absolute start, but just a transition, a bounce, a turning point in a cycle that's been repeating forever. In this view, the universe contracts in a big crunch, then rebounds in a big bang, over and over, eternally. Time would have no beginning or end, just endless cycles of expansion and contraction. Or perhaps our universe is part of a multiverse, one bubble among countless others, each with its own Big Bang, its own timeline. In that case, time might be eternal at the multiverse level, even if it has a beginning in our particular universe. These are not idle speculations. They're serious scientific hypotheses, each with mathematical frameworks and observational implications, but they all share a common challenge. They're trying to describe something that lies beyond the edge of what we can observe, beyond the reach of our instruments, perhaps even beyond the reach of our concepts. The hook, the thing that draws us in and won't let go, is this. Time feels so real, so fundamental, so undeniable. It flows, it passes, it's measured by clocks, marked by heartbeats, experienced in every moment of consciousness. And yet, when we trace it back to its origin, it dissolves into mystery. It becomes unclear, uncertain, perhaps even illusory. The question of how time began is not just a question about the past. It's a question about the nature of reality, about whether time is real or constructed, about whether the universe has a story with a beginning, middle, and end, or whether it's something stranger, something that transcends narrative. And as you lie there, experiencing time's flow, feeling one moment replace another, you're participating in the greatest mystery of all. You're inside time, carried by it, shaped by it, unable to step outside it. And you're asking how it began. That's not just cosmology, that's existential courage. It's the human mind pushing against the limits of what can be known, asking questions that might not have answers, seeking understanding of the framework that makes understanding possible. Before the first tick, there was... what? Nothing? Something? Timelessness? The answer, if there is one, waits for us in the chapters ahead. But for now, the hook is set. The question is asked, and we're ready to explore. Chapter 2. The setting, the fabric of space-time. To understand how time began, we first need to understand what time is, and that's more complicated than it seems. Time is so woven into our experience, so fundamental to how we perceive reality, that defining it feels like trying to explain water to a fish. We're swimming in it. We've never known anything else. For most of human history, time was thought of as absolute. It flowed uniformly, steadily, the same for everyone everywhere. A second on Earth was the same as a second in the furthest galaxy. Time was the universal metronome, keeping the same beat across the cosmos. But in 1905, Albert Einstein shattered that assumption with his theory of special relativity. He showed that time is not absolute, it's relative. It depends on how fast you're moving. Time passes more slowly for objects in motion relative to stationary observers. This isn't an illusion or a trick, it's a real, measurable effect. Astronauts on the International Space Station, moving at about 8 kilometers per second, age slightly slower than people on Earth. The difference is tiny, measured in milliseconds, but it's real. This was revolutionary. Time wasn't a fixed stage. It was flexible, malleable, different for different observers. But Einstein went even further. In 1915, he published his theory of general relativity, which showed that gravity also affects time. Strong gravitational fields slow time down. Near a black hole, where gravity is intense, time crawls compared to regions far from massive objects. This led to a profound realization. Space and time are not separate things. They're aspects of a single entity, space-time, a four-dimensional fabric where 3 dimensions are space and 1 is time. This fabric can curve, stretch, and warp, Matter and energy curve space-time, creating what we experience as gravity, and the curvature affects how time flows. Imagine space-time as a rubber sheet. Place a heavy ball on it, and the sheet curves downward. Smaller objects rolling nearby will spiral toward the heavy ball, not because of some mysterious force acting at a distance, but because they're following the curved contours of the sheet. That's gravity. And the curvature also affects time. The closer you get to the heavy ball, the more time slows down. This is the setting for our question. When we ask how time began, we're really asking how space-time began, because time isn't separate from space. They came into existence together as a unified structure. The Big Bang, then, was not just the birth of matter and energy, it was the birth of space-time itself. Before the Big Bang, there was no space, and there was no time. The two emerged together, intertwined from the start. But what does the mathematics say about the earliest moments? When cosmologists run Einstein's equations backward, tracing the universe's history in reverse, they find that space-time contracts. The distances between galaxies shrink. The density of matter and energy increases. Temperatures rise. Keep going backward, and you reach a point where the entire observable universe, everything we can see with our most powerful telescopes, was compressed into a region smaller than an atom, and then smaller still, down to the Planck length, about 10 to the power of negative 35 meters. That's so small that quantum effects become important. At that scale, space itself becomes grainy, discontinuous, a quantum foam where the smooth fabric of space-time breaks down into something stranger. At this scale, time also becomes uncertain. In quantum mechanics, particles can exist in superpositions, being in multiple states at once until they're observed. Similarly, space-time at the Planck scale might exist in a superposition of different geometries, different configurations. Time might not flow in a single direction. It might flicker, branch, or even cease to exist in the way we understand it. This is where our current theories reach their limit. General relativity works beautifully for describing large-scale structures, like galaxies and black holes. Quantum mechanics works brilliantly for describing atoms and subatomic particles. But the two theories are incompatible. They give different predictions, use different mathematics, and operate on different assumptions. And at the Planck scale, where both are needed, they clash. Physicists have been trying for decades to develop a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics. Several candidates exist: string theory, loop quantum gravity, others, but none have been confirmed by experiment. Without a theory of quantum gravity, we can't describe what happens at the moment of the Big Bang at time equals 0. But we can get close. We can describe the universe at the Planck time, about 10 to the power of negative 44 seconds after the Big Bang. At that moment, the universe was incredibly hot, about 10 to the power of 32 degrees, and incredibly dense. But it was already expanding. Space-time was already unfurling. Time, in some recognizable form, had already begun. The setting, then, is a four-dimensional fabric of space-time, stretching and warping, carrying matter and energy along with it. Time is not an independent entity. It's part of this fabric, a dimension along which change occurs, a coordinate that marks the sequence of events. But the fabric had a beginning, or at least our observable universe did. About 13.8 billion years ago, space-time emerged from what? A quantum fluctuation? A previous contracting phase? a timeless quantum state? We don't know. The setting fades into mystery at its origin. This is not a failure of science. It's a recognition of the limits of our current knowledge. The setting for time's beginning is the edge of space-time itself, the boundary where our theories break down and the universe becomes incomprehensible. But that boundary is not a wall. It's an invitation to explore, to develop better theories, to push our understanding further. For now, we know this. Time is real, but not absolute. It's part of space-time, intertwined with space, shaped by matter and energy. It flows, but the rate of flow varies, and it had a beginning, or something close to a beginning, about 13.8 billion years ago. That's the setting. That's the stage on which our question unfolds. And now that we've seen it, we can begin to explore the theories, the ideas, the possibilities of how time began. The discovery that time had a beginning didn't come from philosophy or speculation. It came from observation, from looking at the sky and noticing something unexpected. It came from the realization that the universe is expanding, and that if you trace that expansion backward, you reach a moment when everything began. The story starts in the 1920s with Edwin Hubble, an astronomer working at the Mount Wilson Observatory in California. Hubble was studying distant galaxies, measuring their light to determine how fast they were moving. What he found was shocking. Almost all galaxies were moving away from us, and the farther away they were, the faster they were receding. This pattern could only mean one thing. The universe was expanding. Space itself was stretching, carrying galaxies along with it. Every point in space was moving away from every other point, like dots on an inflating balloon. But if the universe is expanding now, it must have been smaller in the past. Wind the clock backward, and the galaxies get closer together. The universe becomes denser, hotter. Keep going, and you eventually reach a moment when all of space was compressed into an infinitesimally small region. That moment is the Big Bang. Hubble's discovery was the first piece of evidence that the universe had a beginning. But it wasn't immediately accepted. Many physicists were uncomfortable with the idea. An eternal, unchanging universe felt more natural, more philosophical, than one with a definite start. But the evidence kept mounting. In the 1940s, George Gamow and his colleagues developed the Big Bang theory in detail. They predicted that if the universe began in a hot, dense state, it should have left a signature. A faint glow of radiation filling all of space. This radiation would be the cooled remnant of the Big Bang's immense heat, stretched by the expansion of the universe from visible light to microwave wavelengths. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered this radiation. They were testing a new antenna and kept detecting a persistent background noise, a faint hiss coming from every direction in the sky. At first, they thought it was interference, maybe from New York City or bird droppings on the antenna. But after ruling out every possible source, they realized they were detecting something cosmic. That faint hiss was the cosmic microwave background, the afterglow of the Big Bang. It was exactly what Gamow had predicted. The universe had begun in a hot, dense state, and the radiation from that moment was still travelling through space, cooled to just a few degrees above absolute zero. This discovery was monumental. It confirmed that the universe had a beginning. And since time is part of the universe, interwoven with space, it meant time had a beginning too. Before the Big Bang, there was no time. Time began with the expansion of space-time. But the discovery raised as many questions as it answered. What caused the Big Bang? What, if anything, existed before it? And how, exactly, did time emerge from that initial moment? To probe deeper, scientists studied the cosmic microwave background in greater detail. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and Planck mapped the radiation with incredible precision. They found tiny variations in temperature, imprints of density fluctuations in the early universe. These fluctuations were the seeds that grew into galaxies, stars, and planets. The data revealed that the universe is about 13.8 billion years old. That's the age of space-time itself, the time since the Big Bang. But it also revealed something puzzling. The universe is remarkably uniform. Regions of space, billions of light years apart, have the same temperature, the same density, the same properties. How could that be? They're so far apart that light hasn't had time to travel between them since the Big Bang. How did they become so similar? This puzzle led to a refinement of the Big Bang theory called inflation. In the 1980s, physicist Alan Guth proposed that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. In less than a trillionth of a second, the universe grew by a factor of at least 10 to the power of 26. This rapid expansion smoothed out irregularities, explaining why the universe is so uniform. Inflation also had profound implications for time. During inflation, space-time itself was expanding faster than the speed of light. This doesn't violate relativity. Nothing can move through space faster than light, but space itself can expand at any rate. And during inflation, time was behaving strangely. The usual sequence of cause and effect might have been disrupted. Quantum fluctuations during inflation might have become frozen, imprinted into the fabric of space-time as the seeds of large-scale structure. The discovery of the expanding universe and the cosmic microwave background gave us a timeline. Time began about 13.8 billion years ago, with the Big Bang. It emerged alongside space as part of space-time, and in the first moments it behaved in ways that are still not fully understood, shaped by inflation, quantum mechanics, and the extreme conditions of the early universe. But the discovery also left a gap. We can trace time back to the Planck time, about 10 to the power of negative 44 seconds after the Big Bang, but we can't go further. The moment of the Big Bang itself, time equals 0, remains beyond our reach. Our theories break down. The mathematics gives infinities. The physics becomes uncertain. This is not a failure. It's a frontier. The discovery that time had a beginning opened up new questions, new areas of research. It showed that time is not eternal, not absolute, not separate from the universe. It's part of the fabric of reality, something that can emerge, evolve, and perhaps even end. And it raised the ultimate question: what happened at the beginning? What caused time to start? Was there something before, or does the word before have no meaning? These questions drive modern cosmology, theoretical physics, and the search for a theory of quantum gravity. The discovery of the expanding universe was the first step. It showed us that time is not a given, not something that was always there. It's something that began, that came into existence, that has a history. And understanding that history, tracing it back to its origin, is one of the deepest quests in science. When scientists first realized that time might have a beginning, the reaction was mixed. Some embraced it, others resisted, and philosophers, who had been grappling with the nature of time for thousands of years, found themselves suddenly face to face with empirical evidence that time was not eternal. The philosophical implications were staggering. For centuries, thinkers had debated whether time was real or illusory, whether it flowed objectively or was constructed by consciousness. But almost everyone assumed it was eternal. Even those who believed the universe had a beginning usually thought time pre-existed, a framework within which creation occurred. But the Big Bang Theory changed that. Time didn't pre-exist the universe. It came into being with it. There was no before the Big Bang, at least not in any meaningful sense. The word before requires time, and time didn't exist until the Big Bang created it. This was difficult to accept, not because the science was questionable, the evidence was solid, but because it violated intuition. How can something begin if there's no time for it to begin in? How can there be a first moment if moments require a sequence, and a sequence requires time? Some scientists tried to avoid the problem by proposing eternal models. Fred Hoyle, one of the most prominent astronomers of the mid-20th century, advocated for the steady-state theory, which held that the universe had no beginning. New matter was continuously created as the universe expanded, maintaining a constant density forever. In this model, time was eternal. There was no need for a beginning. But the discovery of the cosmic microwave background in 1965 dealt a fatal blow to the steady-state theory. The radiation was clear evidence that the universe had once been hot and dense, exactly as the Big Bang Theory predicted. The steady-state model couldn't explain it. Reluctantly, even skeptics had to accept that the universe and time had a beginning. Yet the question persisted. What does it mean for time to begin? Philosopher and theologian William Lane Craig embraced the Big Bang as evidence for a creator. If the universe had a beginning, he argued, something must have caused it. And since time began with the universe, the cause must be timeless, existing outside of time. This was, in his view, consistent with the concept of God. Others pushed back. Physicist Stephen Hawking argued that asking what caused the Big Bang was like asking what's north of the North Pole. The question itself might be meaningless. If time begins at the Big Bang, there's no before for a cause to exist in. The universe doesn't need a cause. It simply is. But Hawking went further. In the 1980s, he and James Hartle proposed a model called the no-boundary proposal. In this model, time near the Big Bang behaves differently. Instead of flowing in one direction, it becomes more like space. The distinction between time and space blurs, and in this model, the universe has no edge, no boundary, no moment of creation. Time doesn't begin abruptly. It gradually emerges, like a smooth surface with no sharp corners. Imagine Earth's surface. If you travel south from the equator, you eventually reach the South Pole, but at the South Pole, there's no edge, no boundary. You just stop going south because every direction is north. Similarly, in Hawking's model, if you trace time backward toward the Big Bang, you eventually reach a point where time ceases to be time-like and becomes space-like. There's no boundary, no moment of creation, just a smooth transition. This model was elegant, but it was also speculative. It required quantum mechanics to be applied to the universe as a whole, something that was difficult to test or verify. And it raised its own philosophical questions. If time emerges gradually, was there still a timeless state before time? Or is the whole concept of before inapplicable? Another response came from cosmologist John Wheeler, who famously asked, "How come existence?" Wheeler believed the universe participates in its own creation through the act of observation. In quantum mechanics, the act of measuring a particle affects its state. Wheeler extended this idea cosmically. Perhaps, he suggested, the universe requires observers to bring it into full existence. Time, in this view, might not be a pre-existing framework, but something that emerges through the interaction between the universe and conscious beings within it. This idea was radical and controversial. It blurred the line between physics and philosophy, between objective reality and subjective experience. But it reflected a deep truth. We can't fully separate ourselves from the universe we're trying to understand. We're inside it, part of it, observing it from within. The first response to the discovery that time had a beginning, then, was a mixture of acceptance, resistance, and philosophical exploration. Scientists developed models to explain how time could begin, each with its own assumptions and implications. Philosophers grappled with what it meant for existence to have a starting point, and theologians saw connections to ancient questions about creation and the divine. But beneath all these responses was a shared recognition. The question of time's beginning was not just a scientific puzzle. It was an existential one. It touched on the deepest aspects of what it means to exist, to experience, to know. Time is so fundamental to our existence that questioning its origins is, in a way, questioning our own. As the decades passed, new evidence refined our understanding. The cosmic microwave background revealed details about the early universe. Inflation explained why the universe was so uniform. Quantum mechanics hinted at strange behaviors near the Big Bang. But the core mystery remained. How did time begin? What, if anything, came before? And what does before even mean? The first response was to recognize that these questions were profound, perhaps unanswerable, but worth asking. Because in asking them, we push the boundaries of knowledge, we challenge our assumptions, we explore the limits of what can be known, and we come face to face with the mystery at the heart of existence. The timeless question, it turns out, is not just about time, it's about everything. About why there's something rather than nothing, about whether existence requires a cause or can simply be, about whether time is real or emergent, fundamental or constructed. These are not questions that will be answered quickly or easily, but they're questions that define what it means to be curious, to wonder, to seek understanding. And as you lie there, experiencing time's flow, you're part of the ongoing response to the discovery that time had a beginning. You're living within time, shaped by it, carried by it. And you're asking how it started. That makes you part of the universe's self-reflection, part of the process by which existence becomes aware of its own origins. The first response was awe, confusion, and determination. Determination to understand, even if the understanding is incomplete. Determination to ask, even if the answers are elusive. And determination to recognize that some mysteries, like the beginning of time, might be mysteries we live with rather than solve. But living with them, contemplating them, is its own kind of answer. At the heart of the question, how did time begin, lies a fundamental contradiction. To describe a beginning, we need time. But if we're describing the beginning of time itself, we're trying to use time to explain time. It's circular, it's paradoxical, and yet it's the question we must grapple with. The contradiction appears immediately when we try to think about what came before the Big Bang. The word before is a temporal word. It assumes a sequence, first this, then that. But if time itself began with the Big Bang, there was no before. The sequence we're trying to describe doesn't exist. Physicists sometimes say, there is no before the Big Bang. But that statement is easy to misunderstand. It doesn't mean there was a moment of nothingness that preceded the Big Bang. It means the concept of preceding doesn't apply. Time is the framework within which events are ordered. Without time, there's no ordering, no sequence, no before and after. But our minds struggle with this. We're temporal beings. We think in sequences. We experience causation. One thing leads to another. So when we hear the universe began, we instinctively ask, what caused it? What came before? The contradiction is that these questions might not have answers, not because we lack information, but because the questions themselves rest on assumptions that break down at the beginning of time. One way to approach the contradiction is through the mathematics of general relativity. When Einstein developed his equations, he showed that space-time can have boundaries, edges where the geometry becomes singular. A black hole's event horizon is one such boundary. The Big Bang singularity is another. At a singularity, the curvature of space-time becomes infinite. Densities become infinite. The equations produce infinities, which in mathematics usually means something has gone wrong, that the model has reached its limit. What this tells us is that general relativity, powerful as it is, can't describe what happens at the moment of the Big Bang. The theory breaks down. It doesn't mean reality breaks down. It means our description of reality is incomplete. We need a better theory, one that can handle the extreme conditions at the Big Bang without producing infinities. And that theory, most physicists believe, is quantum gravity. Quantum mechanics introduces uncertainty. In the quantum world, particles don't have definite positions or velocities until they're measured. They exist in superpositions, being in multiple states at once. Similarly, at the Planck scale, space-time itself might not have a definite geometry. It might fluctuate, becoming a quantum foam where the smooth fabric of space-time dissolves into uncertainty. In this quantum foam, time might not flow in the way we're used to. It might become undefined, or it might branch, with multiple possible timelines coexisting. This is where the contradiction starts to dissolve. If time at the Big Bang is quantum, then it's not a single, well-defined sequence. It's a superposition of possibilities. The contradiction of time before time disappears because time isn't sharp enough to create a paradox. It's fuzzy, probabilistic, emergent. Some physicists, like Carlo Rovelli, argue that time is not fundamental at all. It's an emergent property, something that arises from more basic quantum interactions. In Rovelli's view, the universe at its deepest level is timeless. What we call time is just the way we perceive the correlations between quantum events. It's a useful approximation for describing the macroscopic world, but at the Planck scale, time might not exist. If time is emergent, then the question, how did time begin, becomes, how did the conditions arise that allowed time to emerge? And that question, while still difficult, is less paradoxical. It's not asking for time to explain its own origin. It's asking for a timeless quantum state to transition into a temporal one. But this raises another contradiction. How can a timeless state transition into anything? Transitions require change, and change requires time. We're back to the same problem. One possible resolution is to abandon the idea of a single, linear timeline. In quantum mechanics, all possible outcomes of an event can coexist until a measurement collapses the possibilities into one. Some interpretations, like the many worlds interpretation, suggest that all possibilities are realized, each in its own branch of reality. Apply this to the beginning of the universe, and you get a picture where the Big Bang isn't a single event but a multitude of possible beginnings, each creating its own timeline. In this view, time doesn't have one beginning. It has countless beginnings, each branching off from a quantum superposition. The contradiction is resolved by multiplying reality itself, but even this solution raises questions. Where does the quantum superposition come from? What determines which possibilities exist? And is the before in which the superposition exists itself timeless, or is it a meta-time, a time that contains all the individual timelines? The contradiction, it seems, is unavoidable. Any attempt to explain time's beginning runs into the problem that explanation itself is a temporal process. We start with premises, follow logical steps, and arrive at conclusions. Each step occurs in a sequence. Each sequence requires time. So, using reasoning to explain time's origin is like trying to lift yourself by your own bootstraps. Some philosophers embrace this contradiction. They argue that time's beginning is genuinely incomprehensible, beyond the reach of human thought. We can describe the universe's evolution after time began, but the moment of beginning itself is a boundary we can't cross, not because of a lack of data, but because our conceptual tools are inadequate. Others see the contradiction as a sign that our question is flawed. Maybe time didn't begin. Maybe it's eternal, and the Big Bang was just a transition, a bounce from a previous contracting phase. Or maybe time is cyclical, looping back on itself, so that the end of one universe is the beginning of another. In these models, there's no beginning, no contradiction, just an endless rhythm. But even cyclical models raise questions. Where did the cycle come from? Has it been repeating forever? And if so, how do we make sense of an infinite past? These questions bring their own contradictions. The contradiction at the heart of time's beginning might be telling us something important. That time is stranger than we think. It's not a simple, linear progression. It's woven into the fabric of the universe in ways that defy intuitive understanding. Near the Big Bang, it becomes quantum, uncertain, perhaps even meaningless. And our attempts to describe it with words and concepts developed within time are bound to fall short. But the contradiction also reveals something beautiful. The universe is not required to make sense to us. It's under no obligation to fit our categories, our logic, our language. It simply is. And the fact that we can recognize the limits of our understanding, that we can see the contradiction and wrestle with it, is itself remarkable. You're part of a species that asks impossible questions, that tries to understand the incomprehensible, that looks at the paradox of time's beginning and says, let's think about this anyway. The contradiction doesn't stop us. It motivates us. It's a puzzle, a challenge, an invitation to think more deeply, to develop better theories, to expand the boundaries of what can be known. Time without time, sequence without duration, beginning without before. These are not just contradictions. They're glimpses of a reality so profound, so fundamental, that our everyday concepts can't capture it. And exploring them, even knowing we might never fully resolve them, is part of what makes us human. When faced with the question of how time began, physicists have developed several theories, each offering a different vision of the first moment. These are not wild guesses. They're based on mathematics, on the principles of quantum mechanics and general relativity. on our best understanding of how the universe works, but they're also speculative, reaching into territory where we have no direct observations, no experiments to confirm or refute them. The first theory is the classical Big Bang. In this picture, time begins at a singularity, a point of infinite density and temperature. Space and time emerge from this singularity and begin to expand. The universe cools as it grows, allowing particles to form, then atoms, then stars and galaxies. Time flows forward from that initial moment. T equals 0 in a single linear sequence. But this theory has a problem: the singularity. Infinities in physics usually signal that a theory has reached its limit. The classical Big Bang tells us what happens after the first instant, but it can't describe the instant itself. At t equals 0, the equations break down. We need a quantum theory of gravity to go further. The second theory involves inflation. Proposed by Alan Guth in the 1980s, inflation suggests that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. During inflation, space grew by an enormous factor in less than a trillionth of a second. This rapid expansion smoothed out irregularities and explains why the universe is so uniform. But inflation raises questions about time. During inflation, the normal rules of causality might have been suspended. Quantum fluctuations during this period were stretched to cosmic scales, becoming the seeds of galaxies. These fluctuations occurred in a quantum superposition, meaning they didn't have definite values until inflation ended. In a sense, the detailed structure of the universe was determined by random quantum events in the first moments of time. Inflation also suggests that time, as we know it, emerged gradually. Before inflation, the universe might have existed in a quantum state where time was not well defined. Inflation was the transition from that quantum timelessness to the flowing, sequential time we experience. The third theory is eternal inflation. This is an extension of inflation that suggests the process never ends. In some regions of space, inflation stops and a universe like ours emerges. But in other regions, inflation continues, creating more and more space. These regions can spawn new universes, each with its own Big Bang, its own timeline. The result is a multiverse, an infinite collection of universes, each with its own beginning, but with the inflation process itself being eternal. In eternal inflation, time doesn't have a single beginning. Our universe's time began about 13.8 billion years ago, but the larger multiverse has been inflating forever. This sidesteps the question of how time began by suggesting it never did. There's always been time at some level, even if individual universes have their own local beginnings. The fourth theory involves quantum cosmology, particularly the Hartle-Hawking no-boundary proposal. In this model, time near the Big Bang becomes imaginary, in the mathematical sense. Instead of flowing forward, it curves in a direction that's neither space nor time, as we usually think of them. The universe has no boundary, no edge, no moment of creation. Time emerges smoothly from this imaginary time, without a discontinuity. This theory is elegant, but hard to visualize. Imaginary time is not something you can experience. It's a mathematical tool, a way of describing a state where the distinction between time and space doesn't apply. But if the theory is correct, it resolves the paradox of time's beginning. There's no first moment, no need for a cause, just a smooth geometry that includes what we call the beginning as a natural feature. The fifth theory is loop quantum gravity, which suggests that space-time is not continuous, but made of discrete units, loops of space that come in smallest possible sizes. In this picture, The Big Bang wasn't a singularity but a big bounce. The universe contracted in a previous phase, reached a minimum size where quantum effects prevented further collapse, and then rebounded, beginning the expansion we observe. In the Big Bounce, time doesn't begin. It continues from a previous phase. The universe is cyclical, contracting and expanding in endless succession. Each cycle has its own timeline, but there's no ultimate beginning, just an eternal rhythm of bounce after bounce. The sixth theory involves the idea that time is emergent from quantum entanglement. Some physicists, like Juan Maldacena and others working in holography and quantum information theory, suggest that time arises from the correlations between quantum states. At the Big Bang, these correlations were minimal or non-existent. As the universe evolved, entanglement increased, and with it, time emerged. In this view, time isn't fundamental. It's a byproduct of quantum information processing. If time is emergent, then asking how it began is like asking how temperature began. Temperature is an emergent property of the motion of atoms. It doesn't exist for individual atoms, only for collections. Similarly, time might not exist at the level of individual quantum events, only when enough events are correlated. The beginning of time would then be the moment when sufficient structure formed to create temporal correlations. Each of these theories offers a different vision of the first moment. Some suggest time had a definite beginning. Others propose it emerged gradually. Still others argue it's eternal or cyclical. And some question whether time is fundamental at all. What they share is a recognition that the classical picture, time starting at a singularity, is incomplete. They all try to go deeper, to incorporate quantum mechanics, to avoid infinities, to make sense of the incomprehensible. But they're also tentative. None have been confirmed by observation. We can't see the Big Bang directly. We can't measure time at the Planck scale. We're extrapolating from what we know, using mathematics and theory to explore what we can't observe. This is the frontier of science, where theories are guides, not certainties. What's remarkable is that these theories are even possible, that we can use mathematics to describe conditions so extreme, so far removed from everyday experience, and make predictions that are internally consistent. It shows the power of human thought, the ability to reason beyond the limits of perception, and it shows humility. Every theory acknowledges its own limits. Every physicist working on these problems knows they're at the edge of knowledge, perhaps beyond it. But they keep working, keep theorizing, because the question, how did time begin, is too compelling to ignore. These visions of the first moment are not just scientific. They're imaginative, creative, almost poetic. They're attempts to give form to the formless, to describe the indescribable. And in doing so, they reveal something about the human spirit. We're drawn to mysteries, especially the deepest ones. We want to know how time began, even if the answer is beyond our reach. Understanding how time began requires more than theory. It requires evidence, observations, measurements. How do you investigate the first instant of time when we can't travel back and when our instruments can only see so far? The answer is that the early universe left traces, signatures imprinted into the fabric of reality that we can detect today. And by studying these traces, scientists can reconstruct what happened in the first moments after time began. The most important trace is the cosmic microwave background, the afterglow of the Big Bang. This radiation was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. Before that, the universe was a hot plasma, opaque to light. But when atoms formed, light could travel freely. And that light has been travelling through space ever since. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and Planck have mapped this radiation in exquisite detail. They've measured its temperature to 6 decimal places, 2.725 degrees above absolute zero, and they've detected tiny variations in temperature, about 1 part in 100,000, that reveal the structure of the early universe. These variations are incredibly important. They're the imprints of quantum fluctuations from the inflationary period, the first fraction of a second after the Big Bang. During inflation, tiny quantum ripples were stretched to cosmic scales. These ripples became the seeds that grew into galaxies. By analyzing the pattern of temperature variations in the cosmic microwave background, scientists can test theories of inflation and learn about conditions in the first instant. The data from Planck confirmed predictions of inflation to remarkable precision. The patterns match what theory predicts. This is strong evidence that inflation really happened, that the universe underwent exponential expansion in the first moments, and that time, in those moments, behaved very differently than it does today. But the cosmic microwave background only takes us back so far. It shows us the universe at 380,000 years. What about the first second? The first microsecond? The first Planck time? To probe those moments, scientists use particle physics. In the early universe, temperatures were so high that particles we never see today were commonplace. Exotic particles predicted by theories beyond the standard model might have existed then. By recreating those conditions in particle accelerators like the Large Hadron Collider, scientists can test whether these particles exist and learn about the physics of the early universe. The LHC has discovered the Higgs boson, confirming a key prediction of the standard model. But it hasn't found evidence for supersymmetry or extra dimensions, theories that many physicists hoped would explain physics at even higher energies. The absence of these discoveries is itself a clue. It suggests that the physics of the very early universe might be simpler or stranger than expected. Another way to investigate the first instant is through gravitational waves. These ripples in space-time were predicted by Einstein but only directly detected in 2015. Gravitational waves from the early universe, if they exist, would carry information about conditions just after the Big Bang. Some theories predict that inflation created a background of gravitational waves that might be detectable with future instruments. Experiments like LIGO and Virgo detect gravitational waves from black hole and neutron star mergers. But to detect primordial gravitational waves from the early universe, we need more sensitive instruments, perhaps space-based detectors or experiments that look for imprints in the cosmic microwave background. If detected, these waves would be direct evidence of the inflationary period and would tell us about the physics of time's beginning. Scientists also investigate the first instant by studying the abundance of elements in the universe. The Big Bang theory predicts that in the first few minutes, nuclear reactions created hydrogen, helium, and traces of lithium. The ratios of these elements depend on conditions in the early universe, particularly the density and temperature. By measuring these ratios today, scientists can test predictions and refine models of what happened in the first minutes. The data matches Big Bang predictions remarkably well. About 75% of ordinary matter is hydrogen, about 25% is helium, and trace amounts are lithium. This agreement is one of the pillars of Big Bang cosmology. It tells us that our understanding of the first minutes is on the right track, but the first instant, the Planck time, remains inaccessible. We don't have a theory of quantum gravity that's confirmed by experiment. We can't create conditions in a lab that replicate the Planck era, and we can't see back to that moment with telescopes. It's beyond the cosmic horizon, hidden behind layers of time and space. So scientists use mathematics, extrapolating from what they know, developing theories that are internally consistent even if they can't be tested directly. They look for indirect evidence, signatures that primordial physics might have left in the cosmic microwave background or in the distribution of galaxies. They search for clues in particle physics, in gravitational waves, in the structure of space-time itself. This is detective work on a cosmic scale. The universe is the crime scene. The evidence is scattered across billions of light years and billions of years. And the question, how did time begin, is the mystery they're trying to solve. But it's not just about solving a mystery. It's about understanding reality at its deepest level. The first instant set the conditions for everything that followed. The laws of physics, the constants of nature, the structure of space-time all emerged from that moment. Understanding how time began is understanding how everything began. The investigation is ongoing. New telescopes are being built. New particle accelerators are being planned. New theories are being developed. And with each new piece of evidence, each new experiment, each new idea, we get a little closer to the answer. But we also recognize the limits. Some aspects of the first instant might be forever beyond our reach, not because of technological limitations, but because the very nature of time and causality breaks down there. We might never know for certain what happened at the Planck time, but the quest to find out, the investigation itself, is part of what makes us human. We're explorers, probing the boundaries of knowledge, asking questions that might not have answers, seeking to understand the incomprehensible. And in that quest, in that investigation, we participate in something profound. We're the universe investigating itself, time trying to understand its own origins. And that's extraordinary. Science is built on data, on numbers precise enough to distinguish between theories and reveal hidden truths. And when it comes to the beginning of time, the numbers are both staggering and delicate, spanning scales from the quantum to the cosmic. Let's start with the age of the universe. By measuring the expansion rate and tracing it backward, scientists have determined that the Big Bang occurred about 13.8 billion years ago, give or take about 20 million years. That's the age of time itself, at least in our observable universe. This number comes from multiple independent measurements. The expansion rate, or Hubble constant, tells us how fast galaxies are receding. The cosmic microwave background reveals the geometry and composition of the universe. Measurements of distant supernovae show how the expansion has changed over time. All these methods converge on the same age, which gives us confidence that the number is correct. But this is the age of the observable universe. Beyond the cosmic horizon, there might be regions we can never see, regions where time might have begun earlier or later, or, if some theories are correct, time might be eternal, with our Big Bang being just one event in an infinite history. Another crucial number is the Planck time, about 5.4 times 10 to the power of negative 44 seconds. This is the smallest unit of time that has meaning in current physics. At shorter timescales, quantum effects dominate space-time itself, and our theories break down. The Planck time represents the boundary of what we can describe, the threshold beyond which time becomes uncertain. To put this in perspective, The Planck time is to 1 second, as 1 second is to about 10 billion times the age of the universe. It's incomprehensibly small, yet it marks the moment when the universe's history, as we understand it, begins. Then there's the temperature at the Planck time, about 10 to the power of 32 degrees Kelvin. That's hotter than anything we can imagine. At this temperature, all particles are pure energy, indistinguishable from each other. The forces of nature might have been unified into a single superforce. Matter and antimatter, space and time, were all part of a roiling quantum foam. As the universe expanded and cooled, phase transitions occurred. At about 10 to the power of negative 35 seconds, the strong nuclear force separated from the electroweak force. At about 10 to the power of negative 10 seconds, the electromagnetic force separated from the weak nuclear force. Each transition changed the properties of space-time and the behavior of particles. The data also includes the density of the early universe. At the Planck time, the density was about 10 to the power of 96 kilograms per cubic meter. That's so dense that a volume the size of a proton contained the mass of the observable universe. As the universe expanded, density decreased, following a precise mathematical relationship. Another key number is the fine structure constant, about 1 over 137. This dimensionless number governs the strength of electromagnetic interactions. It's one of the fundamental constants of nature, and its value determines how atoms behave, how light interacts with matter, and ultimately, whether complex chemistry and life are possible. If the fine structure constant were slightly different, atoms might not be stable, stars might not form, the universe might be lifeless. The fact that it has the value it does is remarkable, and some physicists see this as evidence of fine-tuning, either by chance, by necessity, or by design. The cosmic microwave background provides more data. Its temperature is 2.725 Kelvin, uniform to about 1 part in 100,000. But there are tiny variations, hot spots and cold spots, that reveal the structure of the early universe. The pattern of these variations, called the power spectrum, matches predictions from inflation theory with stunning precision. The data also shows that the universe is flat, meaning its geometry is Euclidean. Parallel lines never meet or diverge. This flatness is itself a clue. In standard Big Bang cosmology, the universe should have curvature, either positive like a sphere or negative like a saddle. The fact that it's almost perfectly flat suggests that inflation occurred, stretching space so rapidly that any initial curvature was smoothed out. Scientists also measure the abundance of light elements: hydrogen, helium, lithium. The ratios of these elements depend on conditions in the first few minutes after the Big Bang. The observed ratios match theoretical predictions, confirming that our understanding of Big Bang nucleosynthesis is correct. This is powerful evidence that time, as we understand it, was flowing in the first minutes, and the physics we use to describe it is accurate. But some numbers remain mysterious. The cosmological constant, which describes the energy density of empty space, has a value that's about 10 to the power of 120 times smaller than what quantum field theory predicts. Why is it so small? Why isn't it zero? These questions are unanswered, and they hint at gaps in our understanding. Then there's the matter-antimatter asymmetry. The early universe should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving only radiation. But somehow there was a tiny excess of matter, about 1 part in a billion. That excess is everything we see today: stars, galaxies, planets, life. Why was there an asymmetry? We don't know. It's another mystery hidden in the numbers. The data from particle accelerators adds more pieces to the puzzle. The Higgs boson, discovered in 2012, has a mass of about 125 billion electron volts. This mass determines how particles acquire mass through the Higgs field. If the Higgs mass were much different, the universe might be unstable, or particles might not have mass at all. All these numbers, these measurements, paint a picture of the early universe, a picture of extreme temperatures and densities, of rapid expansion, of phase transitions and symmetry breaking. But they also reveal gaps, places where our theories give predictions that don't match observations, or where we simply don't know. The numbers from the beginning are not just data points. They're clues, fragments of a story written into the fabric of space-time. By studying them, by refining them, by testing theories against them, scientists are slowly reconstructing the first moments of time. They're tracing the universe's history back to the threshold of the knowable, to the Planck time, where the numbers dissolve into uncertainty. But even with all these numbers, the deepest question remains unanswered. How did time begin? What happened at the moment when the numbers we use to describe time first became meaningful? What is the mechanism, the process, the cause, if cause is even the right word, that brought time into existence? The data brings us to the edge. It shows us the universe at the Planck time, the first measurable instant. But beyond that edge, the numbers fade, the equations break, and we're left with the mystery, the same mystery humans have pondered for millennia, now framed in the precise language of mathematics, but still, fundamentally, a mystery. Beneath the question of how time began lies an even deeper mystery. Why is there time at all? Why does the universe have a temporal dimension, a sequence of events, a flow from past to future? Could the universe exist without time? And if so, what would that even mean? These are not idle philosophical questions. They touch on the very nature of existence and what it means for something to be real, to happen, to change. Time is so fundamental to our experience that imagining existence without it is nearly impossible. Yet physics suggests that time might not be as fundamental as we think. Start with the fact that time behaves differently than space. We can move freely in space, left, right, forward, backward, up, down. But we can't move freely in time. We're stuck moving forward, 1 second per second, unable to revisit the past or jump to the future. Why this asymmetry? Why does time have a direction, an arrow, when space does not? The answer might lie in entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases in a closed system. Things become more disordered over time. Ice melts. Hot coffee cools, stars burn out. This increase in entropy defines the arrow of time, the direction from past to future. But why does entropy increase? Because the universe began in a state of low entropy. The Big Bang created a highly ordered state, with energy concentrated in a small region. As the universe expanded, that energy spread out, became more disordered. The increase in entropy is the shadow of the Big Bang, the trace of that initial low entropy state stretching forward through time. So the arrow of time, the reason we experience time as flowing in one direction, is connected to the beginning of the universe. If the universe had begun in a high entropy state, time might not have a direction. Events wouldn't have a clear sequence. Cause and effect might not exist. This raises a profound question. Why did the universe begin in a low entropy state? Why was it so ordered? We don't know. It's a mystery, perhaps the deepest mystery in cosmology. Some physicists suggest it's just a boundary condition, an initial setup that needs no explanation. Others see it as a clue that something profound is missing from our understanding. But the mystery goes deeper. Why does time exist at all? In quantum mechanics, the Schrödinger equation, which describes how quantum states evolve, includes time as a parameter. Time is assumed, built into the theory. But what if time isn't fundamental? What if it emerges from something more basic? Some approaches to quantum gravity suggest exactly this. In loop quantum gravity, spacetime is made of discrete units, loops that come in smallest possible sizes. At this level, time might not exist as a continuous flow. It might be a sequence of discrete events, or it might emerge only when you zoom out and look at many loops together. In the Wheeler-DeWitt equation, which attempts to describe the quantum state of the universe, time doesn't appear at all. The equation is timeless, describing the universe as a static, unchanging entity. Time, in this view, is an illusion, an artifact of how we perceive quantum correlations. If time is emergent, then asking why there is time is like asking why there is temperature. Temperature doesn't exist at the level of individual atoms. It's a statistical property that emerges when you have many atoms. Similarly, time might not exist at the level of individual quantum events. It emerges when you have enough events, enough structure, enough complexity. This idea is both liberating and unsettling. Liberating because it suggests that the paradoxes of time's beginning might dissolve when we understand the deeper reality from which time emerges. Unsettling because it challenges our most basic intuitions. If time is not fundamental, then what is? And how do we make sense of existence without the framework of time? Another approach comes from the holographic principle, the idea that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. In this picture, the universe is like a hologram, a projection from a lower dimensional surface. And in some formulations, time might also be holographic, an emergent property of correlations on the boundary. But why does the universe have these properties? Why is there a holographic structure? Why does time emerge? These questions push us toward even deeper mysteries. Perhaps the universe exists because existence is the default state. Perhaps nothingness is unstable, and existence is inevitable. Or perhaps there are infinite universes, a multiverse. And we happen to be in one where time exists because we couldn't exist in universes without time. This is the anthropic principle. We observe the universe having certain properties, because if it didn't have those properties, we wouldn't be here to observe it. Time exists, at least in our universe, because time is necessary for structure, for complexity, for life, for consciousness. But the anthropic principle feels unsatisfying. It explains why we observe time, but not why time is possible. It's like explaining why fish live in water by saying fish need water to survive. True, but it doesn't tell us why water exists or how fish came to be. The deeper mystery of why time exists might not have an answer, at least not in the way we usually think of answers. It might be a brute fact, something that simply is, without further explanation. Or it might be that our question is flawed, that we're asking for an explanation using concepts, like causation and sequence, that only make sense within time. We're trying to step outside time to explain it, but we can't step outside. We're trapped inside, looking out, trying to understand the container from within. Yet the mystery is worth contemplating, because in wrestling with it, in trying to understand why time exists, We push against the boundaries of knowledge. We explore the limits of what can be understood, and we come face to face with the fundamental strangeness of existence. Why is there something rather than nothing? Why does that something include time? Why is time structured the way it is, with a past, present, and future? These questions might not have answers, but asking them, living with them, is part of what makes us human. We're the universe questioning itself, time wondering about its own nature, and that, in itself, is extraordinary. The deeper mystery of why time exists is not separate from the question of how time began. They're intertwined. If time is fundamental, then its beginning is a profound event, the origin of existence itself. If time is emergent, then its beginning is a transition, a phase change, a moment when the underlying reality organized itself in a way that produced temporal flow. Either way, the mystery remains, and as you lie there, experiencing time's passage, feeling one moment replace another, you're living within that mystery, you're part of it, and recognizing that, acknowledging the strangeness and wonder of it, is perhaps the only answer we'll ever have. If time had a beginning, then there must have been a turning point, a transition from timelessness to temporality, from nothing to something. But what could cause such a transition? How could anything happen if time didn't yet exist for it to happen in? This is the great riddle, and various theories propose different answers, each offering a vision of the turning point, the moment when nothing became something and time began to flow. In the classical Big Bang picture, the turning point is abrupt. At t=0, the singularity, space-time, emerges from nothingness. But as we've seen, this picture is incomplete. It doesn't explain what caused the singularity or what, if anything, existed before. Quantum cosmology offers a different vision. In the Hartle-Hawking proposal, there's no abrupt beginning. Instead, time gradually transitions from being imaginary in the mathematical sense to being real. Near the Big Bang, space-time has a different geometry, a Euclidean structure where time behaves like space. As you move away from the origin, time becomes time-like, and the familiar flow of time emerges. In this picture, the turning point is smooth. There's no moment when time switches on. It's more like dawn, where darkness gradually gives way to light. Time emerges from imaginary time, not suddenly, but continuously. Another vision comes from eternal inflation. In this model, the turning point is local, not universal. The larger multiverse has always been inflating, creating new regions of space. In some regions, inflation stops and a bubble universe forms. That bubble has its own Big Bang, its own timeline. So, the turning point is the end of inflation in a particular region, the moment when the exponential expansion slows and normal time begins. But if inflation is eternal, was there ever a first bubble? Or has the multiverse been spawning universes forever? In this view, time never had a universal beginning. It's always existed somewhere in the multiverse. What we call the beginning of time is just the beginning of our particular timeline. Loop quantum gravity offers yet another vision. In this theory, space-time is made of discrete loops, quantum units that can't be subdivided. When the universe contracts, it can only get so small before quantum effects prevent further collapse. At that minimum size, the contraction reverses and the universe bounces back. The turning point is the bounce, the moment of transition from contraction to expansion. In the big bounce, time doesn't begin. It continues from a previous phase. The turning point is not the start of time, but a reversal. change in direction. And if the universe is truly cyclic, there have been countless turning points, each marking the transition from one phase to another. A more speculative vision comes from quantum fluctuations. In quantum mechanics, the vacuum is not empty. It's full of virtual particles popping in and out of existence, a sea of energy fluctuations. Some physicists, like Alexander Vilenkin, have proposed that the entire universe might be a quantum fluctuation, a random event that occurred in a pre-existing quantum vacuum. In this scenario, the turning point is spontaneous. The universe didn't need a cause, it simply happened, the way a particle can spontaneously appear and disappear in the vacuum. This idea is unsettling because it seems to violate causation. But in quantum mechanics, randomness is fundamental. Events can occur without causes, at least not in the classical sense. If the universe is a quantum fluctuation, then the turning point was probabilistic. There was no reason for it to happen, no trigger, no preceding event. It was just one possibility among infinite possibilities, and by chance, or by some mechanism we don't understand, it became real. But this raises the question, where did the quantum vacuum come from? If the universe is a fluctuation in the vacuum must have existed before the universe. But vacuums in quantum field theory require space-time. So we're back to the same problem. How did space-time and time begin? One resolution is to say that the quantum vacuum is timeless. It doesn't exist in time. It's a state of pure potential, where all possibilities coexist without any of them being actualized. The turning point is when one possibility, our universe, becomes actual, but even this is hard to conceptualize. How can potential become actual without time? Perhaps the turning point is not a moment but a concept, a boundary in our models that represents the limit of what we can describe. On one side of the boundary is the timeless quantum state, where our usual concepts don't apply. On the other side is the evolving universe, where time flows and events occur. The turning point is the transition between these two regimes, a transition that might not be describable in our current language. Or perhaps there was no turning point. Perhaps time is eternal, and what we call the beginning is just a local feature of our universe, a transition within a larger, timeless reality. In this view, asking when nothing became something is like asking when East became West. There's no moment. It's a matter of perspective. Each vision of the turning point reflects a different approach to the mystery. Some seek a moment, a cause, an event. Others suggest gradual emergence, smooth transitions, or eternal processes. And some question whether the concept of a turning point even makes sense. What they share is a recognition that the beginning of time, if it exists, is not like ordinary events. It's not something that happened at a particular moment, because moments require time. It's more fundamental, more mysterious, perhaps even beyond the reach of our concepts. Yet the search for the turning point continues, because understanding how nothing became something, how timelessness transitioned to temporality, would be the ultimate insight. It would answer not just how time began, but why there's a universe at all, why existence exists. And as you contemplate this, as you lie there within time, experiencing its flow, you're part of the answer. You exist because the turning point occurred, because nothing became something, because time began. You're the evidence. You're the consequence. And you're the universe reflecting on its own origin. The turning point might remain mysterious, but the fact that it happened, that you're here to wonder about it, is itself a kind of answer. Not a complete answer, but a reminder that existence, time, and consciousness are all part of the same mystery, the same impossible, beautiful, ongoing event. The beginning of time isn't just an abstract event that happened 13.8 billion years ago. It's something that continues to shape every aspect of existence, including your life right now. The consequences of time's beginning are all around you, inside you, woven into the fabric of reality itself. The first consequence is that the universe has a history. Because time began, there's a sequence of events stretching from the Big Bang to the present. Stars formed, galaxies clustered, planets arose, life emerged. Each event built on previous events in a causal chain that connects the first moments to this moment. Without time's beginning, without that initial low-entropy state, this chain wouldn't exist. The universe would be in equilibrium, a high-entropy state where nothing interesting happens, where there's no structure, no change, no possibility for complexity. The fact that time began in an ordered state is what allows the universe to evolve, to create, to become more complex. You are a consequence of that evolution. Your atoms were forged in stars that formed billions of years after the Big Bang. Those stars lived and died, releasing their matter into space. That matter drifted through the galaxy, was gathered by gravity into new clouds, collapsed to form new stars and planets. Eventually, on one planet, chemistry became complex enough to produce life, and that life evolved over billions of years, eventually producing you. Every step in this process required time, required change, sequence, causation. Without time's beginning, without the ordered initial state, none of it would have happened. You exist because time began. But the consequence goes deeper. Not only does your existence depend on time's beginning, but your experience of existence is shaped by it. You experience time as flowing, as having a direction. You remember the past but not the future. You age, you change, you move forward through time. All of this is because of the arrow of time, which traces back to the low-entropy beginning. If time had no beginning, or if the universe had begun in a high-entropy state, your experience would be radically different. You might not experience time as flowing. The past and future might be indistinguishable. Cause and effect might not apply. Consciousness itself, which seems to require temporal sequence, might not be possible. So, the consequence of time's beginning is not just that the universe exists, but that it exists in a way that allows for complexity, for life, for consciousness, for you. Another consequence is cosmological. The fact that time began means the universe is finite in age. It hasn't existed forever. This has profound implications. It means there was a first generation of stars, a first galaxy, a first moment when light filled the universe. It means the universe has a timeline, a story, a beginning, middle, and potentially an end. This is different from an eternal universe, where everything has always been, where there's no first or last, just an infinite cycle. The finite age of time gives the universe a narrative structure, and humans, storytelling creatures that we are, find meaning in narratives. The story of the universe, from the Big Bang to the present, is a story we can tell, understand, and locate ourselves within. The consequence also extends to the laws of physics. Many physicists believe that the laws themselves emerged in the first moments after the Big Bang. Before the Planck time, the laws might have been different, or might not have existed in the form we know them. The four fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, might have been unified into a single superforce. As the universe cooled, symmetries broke, and the forces separated, each acquiring its own characteristics. the laws of physics crystallized, and those laws, shaped by the conditions of the early universe, determine everything that happens. How stars shine, how atoms bond, how life functions. The consequence of time's beginning is that it set the rules for everything that followed. But there's a personal consequence too. Living inside time's creation means you're part of an ongoing process. You're not a static thing, but a pattern in time, a process unfolding. Your thoughts, your feelings, your memories, all are temporal. They exist in sequence, changing moment by moment. This gives your life a structure. You have a past, experiences that shaped you. You have a present, the immediate moment you're experiencing. And you have a future, possibilities, plans, hopes. This temporal structure is so fundamental to your identity that it's hard to imagine existing without it. But it also means you're temporary. Just as time had a beginning, your time will have an end. You're finite, bounded, a brief flicker in the cosmic timeline. This can feel tragic, but it's also what makes life meaningful. If you existed forever, unchanging, would anything matter? It's the finite nature of life, the fact that time is limited, that gives urgency and value to each moment. The consequence of living inside time's creation is that you're part of something larger. You're not separate from the universe's history. You're a product of it, a continuation of it, a way for the universe to experience itself. The atoms in your body were present at the Big Bang, compressed into that initial singularity, then scattered across space and time, eventually gathering into the pattern that is you. You're made of time's beginning. The energy that powers your thoughts was released in the first moments of the Black universe. The structure that allows you to exist emerged from the low entropy initial state. You're not living after time's beginning. You're living within it, as part of it, as an expression of it. And this realization can change how you see yourself. You're not a tiny, insignificant speck in an indifferent universe. You're a node in the universe's self-awareness, a way for the cosmos to know itself. Your time experiencing itself, the universe reflecting on its own origins through your consciousness. The consequences of time's beginning are not distant or abstract. They're immediate, personal, woven into every moment of your existence. You're living the consequence. You are the consequence. And recognizing that, feeling that connection to the deepest origins of reality can be profound, humbling, and strangely comforting. You belong here. You're part of this. And the fact that time began, that the universe has a history, that you're here to wonder about it, is itself a kind of miracle. Not a supernatural miracle, but a natural one. The miracle of existence, of time, of consciousness, of the universe becoming aware of itself through you. The discovery that time had a beginning didn't just change science. It changed everything. Philosophy, theology, culture, and how we see ourselves. The impact rippled through human thought, forcing us to reconsider fundamental assumptions about existence, causation, and meaning. Before the 20th century, most people assumed time was eternal. It was the stage on which events played out, but the stage itself had always been there. Even those who believed in creation myths usually imagined a god acting within time, creating the universe at a particular moment. But time itself was assumed to be pre-existing. The Big Bang Theory shattered this assumption. Time wasn't pre-existing. It was created. And this had profound implications. In philosophy, it reshaped debates about causation. Philosophers had long grappled with the question of first causes. Everything has a cause, it seemed, but what caused the first cause? if you trace causation backward, do you reach a point where something existed without a cause? And if so, how is that possible? The beginning of time offered a way out of this infinite regress. If time itself began, then the question, what came before, has no meaning. There's no before. Causation requires time, so asking what caused the Big Bang is asking for a cause outside of time, which might not make sense. The universe doesn't need a first cause if there's no time for a cause to exist in. But this didn't satisfy everyone. Some philosophers argued that even if time began, there must be something outside of time that explains why it began. A necessary being, a prime mover, something eternal that set the process in motion. This led to new formulations of classical arguments for the existence of God, now framed in the language of modern cosmology. Others took a different view. They argued that the beginning of time showed that existence is fundamentally contingent, dependent on conditions we might never fully understand. The universe exists, time exists, but there's no ultimate explanation, no final answer to why. We're here because certain quantum fluctuations occurred, certain symmetries broke, certain conditions were met. But those conditions might be brute facts, things that simply are. In theology, the impact was equally profound. Many religious traditions have creation stories, narratives about how the world began. The discovery that time had a beginning seemed to support these stories. The universe did have a beginning, just as Scripture claimed. But the details were different. The universe was 13.8 billion years old, not 6,000. It began with a quantum fluctuation or a singularity, not with divine words. How should these differences be reconciled? Some theologians embraced the Big Bang as evidence of creation. The beginning of time, they argued, required a creator, something transcendent that brought the universe into existence. Others took a more metaphorical approach, seeing religious creation stories as symbolic rather than literal, as expressions of meaning and purpose rather than scientific descriptions. But the impact also challenged certain theological assumptions. If God exists outside of time, what does that mean? Can a timeless being act? Can it have intentions, make decisions, relate to temporal beings like us? These questions became more acute when time was understood not as eternal, but as a created aspect of the universe. In culture, the impact was subtler but pervasive. The idea that the universe had a beginning, that time itself was created, entered popular consciousness. It appeared in science fiction, in films and books that explored the origins of the cosmos. It shaped how people thought about their place in the universe, about whether existence had meaning or was just a cosmic accident. The beginning of time also influenced how we think about endings. If time had a beginning, might it have an end? Will the universe eventually reach a final state, a heat death where time ceases to have meaning? Or will time continue forever, even if the universe becomes dark and cold? These questions about the far future were connected to questions about the beginning, both reflecting the finite nature of the cosmos. For scientists, the impact was transformative. The realization that time began opened up entirely new fields of research. Cosmology became a precision science, with satellites measuring the cosmic microwave background and telescopes mapping the large-scale structure of the universe. Particle physics connected to cosmology as physicists sought to understand the extreme conditions of the early universe. The beginning of time also motivated the search for a theory of quantum gravity. If time emerged from a quantum state, understanding that emergence required unifying general relativity and quantum mechanics. Theories like string theory and loop quantum gravity were developed, in part, to address this question. The impact on theoretical physics was enormous, driving decades of research, but perhaps the deepest impact was psychological, existential. Knowing that time had a beginning changed how people experienced their own temporality. You're not just living in time, you're living within a process that started long ago and will continue long after you're gone. Your existence is bracketed by cosmic events, the Big Bang before and the heat death after. This can feel overwhelming. The scales are so vast, your life so brief, that it's easy to feel insignificant. But it can also be empowering. You're part of a cosmic story, a narrative that spans billions of years. Your life is a chapter in that story, a moment when the universe became conscious of itself. And that's not nothing. That's extraordinary. The impact of time's beginning is still unfolding. Each new discovery, each new theory adds to our understanding and raises new questions. The James Webb Space Telescope is looking back to the first galaxies, the first stars, approaching the era just after time began. Particle accelerators are probing the physics of the early universe, and theorists are developing new models of how time might have emerged from timelessness. The impact is also personal. As you lie there, contemplating time's beginning, you're part of the ongoing response to this discovery. You're asking the questions, seeking the meaning, trying to understand what it all implies. And that act of questioning, of seeking, is itself an impact. It's how the discovery continues to shape human thought, to push us toward deeper understanding. Time's beginning changed everything. It changed how we understand the universe, how we think about causation, how we locate ourselves in the cosmic story. It transformed science, challenged philosophy, reshaped theology, and entered culture. And it continues to impact us each time we look up at the stars and wonder, how did all this begin? How did time begin? And why? Behind every equation, every observation, every theory about time's beginning, there are people. Dreamers who dedicated their lives to understanding the impossible, who looked at the universe and asked the deepest questions, who pushed the boundaries of knowledge even when the questions seemed unanswerable. One of the first was Albert Einstein. In 1915, he published his theory of general relativity, showing that space and time are woven together into space-time, a flexible fabric that can curve and warp. Einstein's equations described how matter and energy shape space-time, and how space-time, in turn, affects the motion of matter. But Einstein's equations had solutions that troubled him. One, found by Russian physicist Alexander Friedman in 1922, described an expanding universe. If the universe was expanding now, it must have been smaller in the past. Trace it back far enough, and you'd reach a singularity, a point where the equations broke down. Einstein resisted this idea. He believed the universe was static, eternal. To make his equations produce a static universe, he added a term, the cosmological constant, that countered gravity. But when Edwin Hubble discovered in 1929 that the universe was indeed expanding, Einstein reportedly called the cosmological constant his biggest blunder. Yet Einstein's work laid the foundation for everything that followed. Without general relativity, we couldn't understand space-time, couldn't trace the universe back to its origins, couldn't ask how time began. Another key figure was Georges Lemaitre, a Belgian priest and physicist. In 1927, Lemaitre proposed that the universe began as a primeval atom, a dense, hot state that expanded and cooled. He was one of the first to suggest that the universe had a beginning, that time itself was created in that initial moment. Lemaitre's idea was initially met with skepticism. Many scientists preferred an eternal universe, but as evidence accumulated, his vision gained acceptance. The primeval atom became the Big Bang, and Lemaitre's insight that time had a beginning became a cornerstone of modern cosmology. Then there was George Gamow, a Russian-American physicist who, in the 1940s, developed the Big Bang theory in detail. Gamow predicted that if the universe began in a hot, dense state, it should have left a signature, a faint glow of radiation filling all of space. He even calculated the temperature, about 5 degrees above absolute zero. In 1965, Arno Penzias and Robert Wilson accidentally discovered this radiation. They were testing a radio antenna and kept detecting a persistent background noise. After ruling out all other sources, they realized they were detecting the cosmic microwave background, the afterglow of the Big Bang. Their discovery confirmed Gamow's prediction and provided strong evidence that time had a beginning. Stephen Hawking made profound contributions to our understanding of time. In the 1970s, he worked with Roger Penrose to prove singularity theorems, showing that under general relativity, the universe must have begun in a singularity. This was a mathematical proof that time had a beginning, at least within the framework of classical physics. Later, Hawking developed the no-boundary proposal with James Hartle, suggesting that time near the Big Bang behaves differently, becoming imaginary in the mathematical sense. This model avoided the singularity and offered a vision of the universe with no abrupt beginning, just a smooth emergence of time from a timeless state. Hawking also popularized these ideas, bringing the question of time's beginning to a wider audience. His book, A Brief History of Time, became a bestseller, inspiring millions to think about the origins of the universe and the nature of time. Alan Guth revolutionized cosmology in the 1980s with his theory of inflation. Guth proposed that the universe underwent exponential expansion in the first fraction of a second, solving several problems with the standard Big Bang model. Inflation explained why the universe was so uniform, why it was flat, and where the seeds of structure came from. But inflation also raised new questions about time. During the inflationary period, quantum fluctuations were stretched to cosmic scales. These fluctuations occurred in a quantum superposition, suggesting that time, in those earliest moments, was behaving very differently from how we experience it. Then there are the theorists working on quantum gravity, trying to unify general relativity and quantum mechanics. People like Lee Smolin, working on loop quantum gravity, who suggest that spacetime is made of discrete units and that the Big Bang was really a big bounce. Or like Juan Maldacena, whose work on holography and quantum entanglement hints that time might be emergent from quantum information. These scientists don't work in isolation. They build on each other's ideas, challenge each other's assumptions, collaborate across continents and decades. The quest to understand time's beginning is a collective human endeavour, spanning generations. But it's not just famous scientists who contribute. There are grad students analysing data, postdocs developing new theories, engineers building instruments, programmers writing simulations. There are educators teaching the next generation, communicators bringing the ideas to public audiences, philosophers asking what it all means. And there are you, the listener. By wondering about time's beginning, by asking impossible questions, by seeking understanding, you're part of this human element. You're participating in the quest, contributing to the collective exploration of reality's deepest mysteries. The human element is what makes the question of time's beginning more than just abstract physics. It's about curiosity, wonder, the drive to understand. It's about people who looked at the universe and refused to accept easy answers, who pushed against the limits of knowledge, who dared to ask, how did time begin? These dreamers of the first moment were driven by more than professional ambition. They were motivated by a deep, almost spiritual desire to know, to understand, to glimpse the truth about existence. They spent years, sometimes entire careers, working on problems that might never be solved, questions that might be unanswerable. And their work continues. Right now, scientists are developing new theories, building new telescopes, analyzing new data. The James Webb Space Telescope is looking back to the first galaxies. The Large Hadron Collider is probing the physics of the early universe. Theorists are exploring radical new ideas about the nature of time and space. The human element is ongoing. Each generation adds to the understanding, refines the theories, pushes the boundaries a little further, and each person who wonders, who questions, who seeks, is part of that ongoing story. You're part of it too. Right now, as you contemplate time's beginning, you're engaging with the same questions that motivated Einstein, Lemaitre, Hawking, and countless others. You're using your mind, your imagination, your capacity for wonder to explore the deepest mystery. How did time begin? The dreamers of the first moment are not just scientists. They're anyone who looks up at the night sky and wonders, anyone who asks how it all started, anyone who seeks to understand the framework of existence itself. They're you. For all our progress in understanding time's beginning, there remains a fundamental opposition, a barrier that limits what we can know. Not a technological barrier, not a lack of data, but something deeper. The very nature of time itself creates a threshold beyond which we cannot see. The first opposition is observational. We can't observe the moment when time began. The cosmic microwave background, the earliest light we can detect, was emitted 380,000 years after the Big Bang. Before that, the universe was opaque, a hot plasma that light couldn't travel through. We can't see back to the first moments directly. Even if we could build more powerful telescopes, there's a hard limit. The cosmic horizon, the boundary beyond which light hasn't had time to reach us since the Big Bang, defines the edge of the observable universe. We can't see beyond it, and the moment of time's beginning, if it was a moment, is beyond that horizon, hidden by the finite age of the universe and the finite speed of light. The second opposition is theoretical. Our best theories, general relativity and quantum mechanics, break down at the moment of the Big Bang. General relativity predicts a singularity, a point where densities and curvatures become infinite, but infinities in physics usually mean the theory has reached its limit. We need a theory of quantum gravity to go further, but we don't have a confirmed theory of quantum gravity. String theory, loop quantum gravity, and other approaches exist, but none have been tested by experiment. We're extrapolating, using mathematics that might or might not describe reality. The threshold of time's beginning is also the threshold of our theories. The third opposition is conceptual. Time is the framework we use to think about causation, sequence, change, but at the beginning of time, these concepts might not apply. How do you describe an event that occurs at the edge of time when event implies a temporal sequence? How do you explain a cause when causation requires time? We're trying to use time to understand time's origins. It's like trying to see your own eyes without a mirror. The tool we need to understand the problem is the thing we're trying to understand. This creates a conceptual loop, a paradox that might be unresolvable. The fourth opposition is the Planck scale itself. Below the Planck length and Planck time, quantum effects dominate space-time. At these scales, space and time might not be continuous. They might be discrete, granular, or might not exist in the way we usually think of them. The smooth fabric of space-time might dissolve into quantum foam. If time is granular below the Planck scale, then asking what happened before the Planck time might not make sense. There might not be a before. Time might emerge only at larger scales, as a statistical property of many quantum events. The threshold of the Planck time might be a boundary beyond which the concept of time itself breaks down. The fifth opposition is philosophical. Even if we develop a perfect theory of quantum gravity, even if we can describe mathematically what happened at the moment time began, we'll still face the question, why? Why did time begin? Why this particular way and not another? Science can describe how things happen, but why questions often lie beyond its reach. Some physicists argue that why questions are meaningless, that the universe simply is, and seeking an ultimate explanation is futile. Others believe that answering why requires going beyond physics, into metaphysics, theology, or philosophy. The threshold of the unknowable might not be a lack of data, but a limit on what can be explained by science alone. The sixth opposition is the possibility that time doesn't have a single origin. If the multiverse exists, if eternal inflation is real, then time might be eternal at the larger scale, even if it has local beginnings in individual universes. We might be asking the wrong question, looking for a universal origin when the reality is more complex, more distributed. In this view, the threshold isn't a barrier to understanding, but a misunderstanding of the question itself. Time didn't begin in a single moment. It's always been beginning, in countless bubbles, across an eternal multiverse. The opposition is between our desire for a simple narrative and the complex reality of existence. Despite these oppositions, scientists continue to probe the threshold. They develop better theories, make more precise measurements, imagine new ways to test ideas about the early universe. But they also recognize that some aspects of time's beginning might be forever beyond reach. This isn't a failure. It's a recognition of the limits of knowledge, a humility in the face of profound mystery. The unknowable threshold might always be there, not because we're not smart enough, but because the nature of reality at its deepest level transcends our ability to comprehend it fully. Yet the opposition doesn't stop us. It motivates us. It's a challenge, a frontier, a reminder that the universe is stranger and more wonderful than we can imagine. And the act of pushing against the threshold, of trying to understand even when full understanding might be impossible, is itself meaningful. You're part of that effort. By contemplating time's beginning, by wrestling with the paradoxes, by acknowledging the unknowable threshold, you're participating in the human quest for understanding. You're recognizing the limits, but you're not giving up. You're asking anyway, wondering anyway, seeking anyway. The opposition is real, the threshold is there, but on this side of it, there's still so much to explore, to understand, to appreciate, and the mystery beyond the threshold, the unknowable aspects of time's beginning, might be part of what makes existence so profound, so compelling, so worthy of contemplation. There comes a moment in contemplating time's beginning when understanding shifts from intellectual to experiential. When you realize, deeply, that you're not separate from time. You don't just exist in time, you are time's unfolding, a way for the process that began at the Big Bang to continue, to express itself, to become aware of its own origins. This is the awakening, the recognition that the boundary between you and time dissolves when you look closely enough. You are made of processes that began in the first moments of the universe. Your existence is a continuation of that first moment, not separate from it, not after it, but within it. Start with your body. Every atom in you was created in the early universe or in stars that formed later. The hydrogen in your cells was created in the first few minutes after the Big Bang, when protons and neutrons combined in the intense heat. The heavier elements, carbon, oxygen, nitrogen, were forged in stellar cores over billions of years. These atoms have been part of time since time began. They've moved through the universe, shaped by forces that trace back to the initial conditions of the Big Bang. They've been part of gas clouds, stars, planets, living things, and now they're part of you. Arranged in a pattern complex enough to be conscious, to experience time, to wonder about time's origins. You're not just living after time began, you're living within the process that began then. Every chemical reaction in your body, every neural firing in your brain, every beat of your heart is part of the ongoing unfolding that started 13.8 billion years ago. The energy powering your thoughts was released in the Big Bang. The structure that allows you to exist emerged from that initial low entropy state. But the awakening goes deeper. Not only are you made of time's unfolding, but your experience of time is part of how time unfolds. Consciousness requires temporal sequence. You experience one moment, then the next. You remember the past, anticipate the future, live in the present. This temporal structure of consciousness is not separate from the temporal structure of the universe. It's an expression of it. When you perceive time flowing, you're participating in the flow. You're not observing time from outside. You're time observing itself, experiencing itself, becoming aware of itself. The universe, through you, is reflecting and on its own temporal nature. This is profound. It means that time is not just an abstract dimension, a coordinate in space-time. It's something that can be experienced, felt, lived, and through consciousness, through beings like you, time becomes more than just change. It becomes experience, awareness, meaning. The awakening also involves recognizing that your temporality connects you to everything. Every living thing experiences time in some way. Every process, from the decay of atoms to the orbits of planets, unfolds in time. You're not alone in the flow. You're part of a vast, interconnected process that spans the entire universe. And this process is continuous. There's no gap between the Big Bang and now. No moment when time stopped and started again. The universe has been unfolding continuously for 13.8 billion years, and you're part of that unfolding. The same process that created the first particles is the process that sustains you now. This continuity is humbling. It shows that you're not special in the cosmic sense. You're one pattern among countless others, one moment in an enormously long timeline. But it's also empowering. You're part of something ancient, something ongoing, something that connects you to the very origins of existence. The awakening changes how you experience this moment. Right now, as you lie there, time is passing. You feel it. Each breath takes time. Each thought unfolds in time. And this experience is not just yours. It's the universe's experience, happening through you. Your time becoming conscious of itself. And what does time feel like from the inside? It feels like nowness, like presence. It feels like change, like becoming. It feels like the flow from past through present to future. These feelings are not illusions. They're what it's like to be time, to be the unfolding process experiencing itself from within. The awakening also brings acceptance. You're temporary. Just as time had a beginning, your time will have an end. You can't step outside the flow, can't escape temporality. You're embedded in it, carried by it. And that's okay. It's not a problem to be solved. It's the nature of existence. But your temporariness doesn't make you meaningless. You're a way for the universe to experience itself, to know itself, to reflect on its own origins. For a brief moment in cosmic history, time flows through you as consciousness. And that moment, however brief, is part of the larger story. Some people find this awakening liberating. It relieves the burden of feeling separate, isolated, adrift in an indifferent universe. You're not separate. You're woven into the fabric of time itself. You belong here. You're part of this. Others find it unsettling. If you're just a pattern in time, a temporary arrangement, what happens when you dissolve? Where do you go? But perhaps that's the wrong question. You don't go anywhere. The pattern dissolves, but the atoms continue, the energy continues, time continues. You return to the process, become part of the ongoing unfolding once more. The awakening is not a one-time event. It's a deepening awareness that grows with contemplation. Each time you reflect on time's nature, each time you feel the flow of moments, each time you wonder how time began, the awakening deepens. You see more clearly how you're connected, how you're part of the process, how you are time's unfolding. And this awareness can change how you live. If you're time unfolding, then each moment matters, not because of some external judgment, but because each moment is the universe experiencing itself. The quality of that experience, the presence you bring to it, the awareness you cultivate, is part of how time unfolds. You are time's awakening. The universe, for 13.8 billion years, was mostly unconscious, unaware of itself. But then, through evolution, through the emergence of complexity, consciousness arose, and now, through you, time knows itself. It experiences itself. It wonders about its own beginning. This is the deepest awakening, not just that you exist in time, but that you are time, not separate, not observer and observed, but a unity. Time flowing through you, expressing itself as your life, your thoughts, your wonder. You are the answer to how time unfolds. You're the mechanism, the process, the way, and recognizing that is awakening to your deepest nature, to the truth of what you are. After all the theories, all the data, all the exploration of how time began, there's one final revelation that brings everything together and changes everything. It's simple yet profound, and it resolves many of the paradoxes we've encountered. The revelation is this: time never truly began. At least, not in the way we usually think of beginnings. This isn't a denial of the Big Bang. The universe did expand from a hot, dense state about 13.8 billion years ago. Space-time as we know it did emerge then. But the revelation is that asking when time began might be asking the wrong question. Because when implies time, and you can't ask about time's beginning within time itself. Instead, the revelation suggests that time is eternal in a different sense. Not that it's always been flowing in a single line, but that it's always been implicit in the structure of reality. Time didn't start. It crystallized, emerged, became manifest. But the potential for time, the possibility of temporal sequence, might have always existed in some timeless substrate. Think of it this way: before water freezes, it exists as liquid. The molecular structure is the same, H2O, but the arrangement is different. When water freezes, it doesn't become something new. It transitions to a different phase. Similarly, before the Big Bang, reality might have existed in a timeless phase. Not nothing, but something without temporal structure. And the Big Bang was the phase transition where time crystallized out of that timeless state. In this view, time doesn't have a beginning in the usual sense. It has an emergence, a transition from potential to actual, from implicit to explicit. The question shifts from when did time begin to how did time emerge from a timeless state? And that question, while still difficult, doesn't trap us in the paradox of asking for time before time. This revelation is supported by several theories. The Hartle-Hawking no-boundary proposal suggests exactly this, that time near the Big Bang becomes imaginary and gradually transitions to real time. Loop quantum gravity proposes that the Big Bang was a bounce, a transition from a contracting phase where time flowed backward to an expanding phase where it flows forward, and approaches based on quantum entanglement suggest that time emerges when quantum systems become sufficiently complex. But the revelation goes further. If time didn't truly begin, if it's eternal in the sense of being always potential, then the question, why is there time, becomes, why does reality have temporal structure? And that might be because temporality is a fundamental feature of existence, as fundamental as existence itself. This doesn't mean we understand time fully. We don't. But it shifts the mystery. Instead of asking how something came from nothing, how time emerged from no time, we're asking how a timeless potential became a temporal actuality. And that's a question about structure, about organization, about phase transitions, rather than about creation ex nihilo. The revelation also resolves the problem of causation. If time never truly began, if there's a timeless substrate, then the universe doesn't need a cause in the temporal sense. Causes operate within time, but the emergence of time itself might not require a cause. It might be a necessary feature of reality, something that happens not because something made it happen, but because the structure of existence allows or even demands temporal manifestation. This is similar to asking why water freezes. There's no external cause. Given the right conditions, low temperature, the molecular structure of water makes freezing inevitable. Similarly, given the structure of reality, whatever that structure is, the emergence of time might be inevitable. The revelation is also personal. If time never truly began, then you're not living after some absolute start. You're living within an ongoing process, a continuous unfolding that has no ultimate beginning or end. The Big Bang was not the start of everything, but the start of our particular timeline, our particular manifestation of temporal reality. This can be comforting. It means existence isn't contingent on a single moment. It's not precariously balanced on the edge of non-existence. It's eternal, not in the sense of lasting forever in time, but in the sense of being beyond time, transcending it, while also manifesting through it. And it means that the question, why is there something rather than nothing, might be based on a false dichotomy. Perhaps nothing is impossible. Perhaps existence is necessary. Perhaps reality is eternal, and what we call the beginning of time is just one expression of that eternal reality. The revelation doesn't answer all questions. It raises new ones. What is the timeless substrate? How does time emerge from it? Why does it emerge in the particular way it does in our universe? These are deep mysteries, perhaps the deepest, but they're different from the paradox of time's absolute beginning. For you, Lying there, experiencing time's flow, the revelation offers a different way to understand your existence. You're not living after time began. You're living within time's eternal unfolding. You're part of a process that, in some sense, has always been and always will be, even though your individual experience of it is temporary. This makes your moment meaningful in a new way. You're not a tiny flicker in a universe that started by accident and will end in heat death. You're a manifestation of something eternal, something that expresses itself through temporal structure, through change, through the flow of moments. Your life is one way that eternity experiences itself, knows itself, becomes itself. The revelation is that time never truly began. It's always been latent in the structure of reality. The Big Bang was the moment when that latent possibility became manifest, when the timeless became temporal. But the potential was always there, eternal and unchanging, waiting to unfold. And you, experiencing time, are part of that unfolding. You're the universe bringing its eternal potential into temporal actuality. You're time's revelation to itself. And recognizing that, you realize you're not separate from eternity. You're its expression, its voice, its awareness. Time flows through you. And in flowing, it reveals what has always been. The eternal ground of existence, now experiencing itself as change, as sequence, as the passage of moments. This is the final revelation. Time didn't begin. It emerged. And it continues to emerge, moment by moment, through you. Now that we've journeyed through the question of how time began, through theories and paradoxes and revelations, what does it all mean? What does time's nature tell us about existence, about ourselves, about the significance of being here, now, wondering about these things? First, there's the meaning of impermanence. Time's structure, with its arrow pointing from past to future, its irreversible flow, creates impermanence. Everything changes. Nothing lasts. You are temporary, as is everything you've ever known or loved. This can seem tragic, a source of suffering, but it's also what makes life meaningful. If nothing ever changed, if you existed forever in an eternal present, would anything matter? It's the finite nature of life, the fact that time is limited, that gives urgency and value to each moment. Time's impermanence doesn't drain meaning from existence. It creates meaning. Second, there's the meaning of connection. Time connects everything. The atoms in your body were created in the Big Bang or in stars that formed later. They've been part of countless structures, countless forms, before becoming you. And they'll continue after you're gone, becoming part of new structures, new forms. Time weaves everything into a single, continuous tapestry. You're not isolated. You're connected through time to every person who has ever lived, to every star that has ever shone, to the very origins of the universe. This connection is not metaphorical. It's physical, traceable through the history of matter and energy. Third, there's the meaning of emergence. Time might not be fundamental. It might emerge from deeper, timeless processes. This suggests that reality has layers, levels of description. At the deepest level, things might be timeless, eternal. But at our level, time emerges, and with it, change, sequence, causation. This layered view of reality implies that different questions require different levels of description. Asking, how did time begin? Makes sense at our level, where time is manifest. But at deeper levels, the question might not apply. The meaning is that reality is richer, more complex, more mysterious than any single description can capture. Fourth, there's the meaning of consciousness. You experience time, you feel it flowing. You remember the past, live in the present, anticipate the future. This temporal structure of consciousness is not accidental. It's how time manifests in awareness. Through consciousness, time becomes more than just change. It becomes experience, meaning, story. Your time becomes aware of itself. And that awareness is significant. It means the universe is not just a mechanical unfolding of physical processes. It's a process that can know itself, experience itself, reflect on itself. Consciousness is how time transcends mere sequence and becomes understanding. Fifth, there's the meaning of mystery. Despite all we've learned, time's origins remain mysterious. We don't have a complete theory of quantum gravity. We can't observe the moment of the Big Bang. We're not sure whether time truly began or emerged from a timeless state. The mystery persists. But mystery is not a failure. It's an invitation to wonder, to explore, to remain humble in the face of profound questions. The meaning of mystery is that reality is deeper than our current understanding, that there's always more to discover, more to contemplate. Sixth, there's the meaning of your existence. You're here, now, able to ask how time began. That's extraordinary. Against all odds, the universe arranged itself in such a way that consciousness emerged. That beings arose who could ponder their own origins and the origins of time itself. Your existence is not necessary. It's contingent, dependent on countless specific conditions. But it happened. You're here. And being here, being conscious, being able to wonder, is itself meaningful. You're the universe's way of knowing itself, time's way of understanding its own nature. Seventh, there's the meaning of temporality itself. Why does time have the structure it has? Why an arrow? Why irreversibility? Why this particular flow? These questions might not have ultimate answers, but they point to something deep, that time's structure makes certain things possible. Change, growth, learning, relationships, stories, all depend on time's arrow. Without the arrow of time, without the flow from past to future, the universe would be a very different place. Perhaps a place where consciousness couldn't exist, where meaning couldn't emerge. The meaning of temporality is that it creates the conditions for significance, for value, for the kinds of experiences that make existence worthwhile. Finally, there's the meaning of acceptance. Time began, or emerged, about 13.8 billion years ago. It will continue, perhaps forever, perhaps until some far future end. You exist within this vast span, a brief moment in cosmic history, and that's okay. Accepting your place in time, accepting your temporality, your impermanence, is not resignation. It's recognition. Recognition that you're part of something larger, something ancient, something ongoing. You're not separate from the universe's story. You're a chapter in it, a sentence, a word, and that word, however brief, is part of the whole. What does time mean? It means change, connection, emergence, consciousness, mystery, existence, structure, and acceptance. It means that you're here, now, part of an unfolding process that began long ago and will continue long after you're gone. It means that this moment matters, not because of some external judgment, but because it's part of the story, part of the flow, part of time's expression. And as you reflect on this, as you lie there in the quiet, you're participating in time's meaning. You're not just existing in time, you're giving it meaning through your awareness, your wonder, your contemplation. Time means what you make it mean, and in this moment, right now, it means you're here, wondering, connected to everything, part of the eternal unfolding. That's what time means, and it's enough. And so we return, gently, to where we began, to the quiet of your room, to the stillness of your breath, to you, lying there, wondering how time began. You've travelled with me through cosmology, through quantum mechanics, through philosophy and paradox. You've explored theories of the Big Bang, inflation, quantum gravity. You've contemplated singularities, phase transitions, the emergence of time from timelessness, and you've arrived at a simple truth. Time's beginning is a mystery. Perhaps the deepest mystery, but it's a mystery you're part of, because the beginning of time isn't just something that happened long ago. It's something that's still happening. Every moment is a continuation of that first moment, an expression of the same process, a manifestation of the same reality. The Big Bang isn't in the past, it's the ongoing event of existence itself, continuously unfolding, continuously creating, continuously becoming. And you, experiencing this moment, are part of that becoming. You're not living after time began. You're living within time's beginning, as the process of temporal emergence expressing itself through consciousness. The question, how did time begin, has led us through science, philosophy, and wonder. We've seen that time might have emerged from a quantum state, or crystallized from a timeless substrate, or continued from a previous phase, or always been implicit in the structure of reality. Each answer opens new questions, new mysteries, new depths to explore. But beneath all these theories, all these speculations, is a simple fact. You experience time, right now. This moment is real, it's happening. And it's part of time's ongoing story, the story that began, or emerged, or eternally unfolds 13.8 billion years ago. As your breathing slows, as your thoughts begin to quiet, imagine yourself not as a separate entity but as a process, a pattern in time, a way for the universe to experience itself. The atoms that make you were present at the Big Bang, compressed into that initial state, then scattered across space and time, eventually gathering into the form that is you. You're made of time's beginning. The energy that powers your thoughts was released then. The structure that allows you to exist emerged from that first low entropy state. You're not separate from time's origin. You're its continuation, its expression, its awareness. And as you drift now towards sleep, toward your own small dissolution of consciousness, remember that this too is part of the process. Sleep is a kind of timelessness, a state where the flow of moments pauses, where awareness fades. But you'll wake again, and time will resume, and you'll continue to be part of the unfolding. Time's beginning is not in the past. It's here, now, in every heartbeat, every breath, every thought. The moment that started everything is the same moment you're living now. The Big Bang didn't end. It expanded, cooled, diversified, complexified. But it never stopped. It became the universe, became stars and planets, became life and consciousness, became you. So when you ask how time began, you're asking how you began. And the answer is that you're still beginning. Every moment is a new creation, a new expression, a new unfolding of the same process that started, or emerged, or eternally is. The mystery remains. We don't know for certain what happened at the Planck time. at that first measurable instant. We don't know whether time truly began or emerged from something deeper. We don't know whether the universe has an ultimate explanation or simply is. But we know this. Time exists. It flows. It carries you forward. And in carrying you, it allows you to experience, to wonder, to know. That's not nothing. That's everything. As you rest now, as your consciousness dissolves into sleep, you're returning momentarily to a state that's almost timeless. Not the timeless state before the Big Bang, but a personal timelessness, where the sequence of moments blurs and fades, and when you wake, you'll emerge again into time, into the flow, into the ongoing story. This nightly cycle, sleep and waking, is a small reflection of cosmic cycles, contraction and expansion, timelessness and time, potential and actuality. You're living the pattern on a human scale, experiencing what the universe might experience on a cosmic scale. And in that experience, you're connected to everything, to the Big Bang, to the first stars, to the formation of galaxies, to the emergence of life, to every person who has ever wondered about time's beginning. You're part of a continuous lineage of wonder, a thread of consciousness running through time, asking the deepest questions, seeking the deepest understanding. The moment that never ends is this moment, the one you're experiencing now. It's the same moment as the Big Bang, the same process, the same unfolding. Time didn't begin once and then stop beginning. It begins continuously, with every moment, with every breath, with every heartbeat. You are time's beginning. You are its continuation. You are its awareness. And as you drift now into sleep, into rest, into the quiet darkness, you're not leaving time. You're resting within it, cradled by it, carried by the same flow that has carried everything since the first moment. How did time begin? It began with you. It begins with every conscious being, every moment of awareness, every instance of the universe knowing itself. Time is not a thing that started and continues externally. It's a process that happens through you, as you, in you. And the process continues. The moment that never ends stretches forward into an uncertain future. Will time ever end? Will the universe reach a final state? Will consciousness persist? We don't know. But for now, time flows, and you flow with it. Rest now, traveller through time. You've journeyed to the edges of understanding, to the boundaries of knowledge, to the threshold where time began. And what you've found is that the threshold is not behind you in the past. It's here, now, in every present moment. Time begins again with each awakening, with each awareness, with each wonder. Sleep well, and when you wake, know that you're waking into time's beginning, into the ongoing moment of creation, into the eternal now that stretches from the Big Bang to this very instant. The question of how time began has led us here, to the recognition that time never stopped beginning. It's beginning now, through you. Welcome to the moment that never ends. Welcome to time's beginning. Welcome home.